chapter 5. And in doing that, in the last lecture, we did all the things except one. One is Lyapunov stability. So, in the last lecture, we briefly reviewed some part of chapter 3 that this is Lyapunov equation. And we have seen that this is kind of linear operation. Some linear matrix A and M equal to C. So, the eigenvalue of A, this matrix operation, eigenvalue of this matrix is sum of the eigenvalue of this and sum of eigenvalue of that. So eigenvalue of this was sum of eigenvalue of A plus sum of eigenvalue of B. That was the eigenvalue of this matrix A. And we have seen that what's the positive definite? We have seen the definition of positive definite, whether a matrix A is positive definite or not. The definition was, if for a given matrix A, if x, any vector except 0, if this is 0, this is always 0. So any vector except 0, for all vectors, non-zero vectors, if those are satisfied, then we say A matrix is positive definite. And we have seen that if A matrix is positive definite, it's the same to A can be decomposed to other matrices. Let's say B, for example. It can be decomposed to B transpose B such that B is non-singular. Okay. So those are the contents of chapter 3. And now we will go back to chapter 5 and we will see what's the Lyapunov stability. So let me write theorem 5.5. All eigenvalues of A has negative real parts if and only if given any past definite symmetric matrix and the Lyapunov equation of A transpose M plus MA equal to minus N has a unique symmetric solution M, and M is positive definite. Okay. This is about Lyapunov stability of matrix A. For given, for example, if A is given like this. So there is some initial condition and 0 input. Then whether the system will converge to 0 or the system response will be bounded or not can be decided by checking this theorem. And if we see the theorem, Okay, you need to write it down. If you see the theorem, all eigenvalues of A has negative real parts, which means that A is stable. All eigenvalue of A has negative real parts means A is stable. If and only if given any positive definite symmetric matrix N. So if you give any positive definite symmetric matrix N, then if Lyapunov, this kind of Lyapunov equation has solution of the M, and such that it's unique, symmetric, and positive definite, then A is stable. In other words, A is stable if this Lyapunov equation is satisfied for any N. N could be any arbitrarily positive definite matrix. Given that N, if we are able to find M such that unique, symmetric, positive definite, in case those M exist for any N, then A is stable. That's what this theorem says. So let's say this blue part if those something is satisfied, then red part A is stable. If you see this theorem in this way, we can see that in another way because it's if and only if. But if I take a viewpoint of this kind of viewpoint, if this is satisfied and this is stable, then I can prove the necessity. Necessity proof is done in a way that I assume this. Okay, I start from A is stable. Then let's see whether I start from here, A is stable, and let's see whether there exists M, there exists such M, and whether M is solution, and let's see whether M is symmetric, and let's see whether M is unique. Then it's necessity proof. Assume that A is stable. Then we will see whether there exists such M for given any N. There exists such M. And that M is a solution. And that M is symmetric. And that M is unique. We will see one by one. Okay, starting from A is stable. A is stable, so A has all negative real parts. And first, let's see, there exists M. Okay, first, this equation is special case of this Lyapunov equation that here A is substituted to A transpose. Here B is substituted to A. And C is substituted to minus N. So this form is special case of general Lyapunov equation. That means we might be able to describe it in a way that such a matrix and some M matrix equal to minus N in this way, similar to this. then the eigenvalue of this matrix is eigenvalue of this matrix is sum of eigenvalue of A transpose from A transpose and sum of eigenvalue of A. But naturally, eigenvalue of A transpose and A should be the same. So its eigenvalue are the same to this. So I may write it mu instead of, I may write it lambda instead of mu. So they have the same eigenvalues. And we know that A is stable, so we know that they are negative. They have negative real parts. That means we are not able to find any set of lambda. There's no ij that satisfies its eigenvalue to be nothing. So its eigenvalue is not nothing. That means it's non-singular. Okay? If it's non-singular, then it means it's full rank. Non-singular. And we can do the inverse. Then we can find solution. We can find solution M in this way. So we know that there exists solution. Okay, we know that there exists solution. Number 3, M is solution. Then what kind of solution is possible? What type of M could be the solution? Here we assume that, let's claim that M is given N and given A. N and A is given. N is arbitrary and A is from system equation. Then let's claim that M takes this kind of form. And let's show that this is correct form. Then if we put this equation to Lyapunov equation, then there appears A transpose. And if I mark it in red, A transpose can go inside to the M. So from 0 to infinity, plus A is here, equal to if we calculate, it should be minus n. If this red is solution, then it should be minus n. And let's see whether this makes minus c or not. Then we can easily check out that this is differential of this form. If we do the differentiation to this term, then we get these two different terms. Then this is evaluation of from 0 to infinite. N. Then, if we put infinite, t to infinite here, then as you know that, as you assume that A is stable, so if you put infinite, this term and this term will converge to nothing because A is stable. So for the infinite case, it's nothing. If I put nothing, 0 here, E nothing is 1, E nothing is 1, so this is minus n. So what happened is that this is equal to minus n. That means if I select m in this way, and if I put it here, then minus n appears. That means this form is possibly one of the solutions. Possibly one of the solutions. Not possibly, it's definitely one of the solutions. But we do not know whether it's unique or not, but one of the solutions. Because this satisfies this Lyapunov-ification. And if we want to see M is symmetry, for M is symmetry, M symmetry, then here n is symmetric. We selected m in this way. Here n is symmetric by given condition. N is symmetric. And this is quadratic form, so it does not change the symmetric form. Therefore, if this is symmetric, this should be symmetric. So if we take m in this way, then m is symmetric. If m is given like this. Because n is symmetric. Because inside term is symmetric and this is quadratic form, which does not hurt the symmetric form. So m is symmetric. Final one is this unique solution unique? Okay, let me use this part, unique. Uniqueness. Let's assume that there are two solutions, M1, M2, that satisfy this equation. Then M1 and 2, there's M1 for given n, and another solution, M2. Then we may do the subtraction for those two equations. Then it will give A transpose M1 minus M2 plus M1 minus M2, A equal to nothing. Okay. And let's multiply. In the front, multiply E, A transpose T. And in the back, let's multiply E, AT. Then it's similar to this form. AT, E, A transpose T, E, AT in the end is similar to this form. So it's also turned out to be differential of other form. Then we can easily see that if we multiply red part, then the whole equation is equal to differential of whole equation is equal to this form. Now let's integrate it. From 0 to infinity. If we integrate it, then it's integration of inner part. This integration of from 0 to infinity, where if we put infinity in here, it's nothing. The whole term is nothing because A is stable. So for infinity, it's nothing. Whole term is infinity. And for if we put 0, then other things disappear. This is 1, this is 1. Only remaining is m1 minus m2. Equal to nothing. Which means, if this is nothing, that means m1 is equal to m2. That means there's unique solution. Initially, we assume that there are two solutions, m1 and m2. Initially, we assume that there are two solutions. And we put it and calculate did some tricks, and finally appears to be the same. That means this m is unique solution. So this m is unique solution. So in this way, we prove that if all eigenvalues of A has negative real part, then for any arbitrary positive symmetry n, this Lyapunov equation is satisfied. Actually, this is not used for linear system because this proof is its utilization for linear system is a little bit tricky, not simple. Rather than check the eigenvalue, that's more simple. But if you go to nonlinear system, you may need this kind of Lyapunov stability proof. So it will be utilized for the nonlinear system when you prove Hurwitz stability or something like that. Okay, so from this point you may start the nonlinear system. So we are done with the stability. Any questions? Okay. Then chapter 5 is done. We have one last chapter. Chapter 6. Chapter 6 is controllability and observability. Controllability, that means control. Whether I can do the control or not. Controllable or non-controllable. And observability. Observe that given output, we detect the given output whether or not we can detect the inner internal state or not. So let's see one example. Okay, let's say there is this kind of circuit. Then the voltage from here to here is set to be x1. And the voltage here to here is set to be x2. And input is some current source. And we detect y here. The detection measurement is done on here. So this is a linear system. Any RLC circuit is linear system. So this is linear system. Then, by adjusting U, by changing U, can we set x1 and x2, whatever we want, to any arbitrary value that we want? Then it's controllable. By adjusting U, if we can send x1 to any state as well as x2 to any state, then the system is controllable using U. However, in this system, x2 cannot be controlled by you. It's not controllable. Whatever u is given, x2, we cannot change x2 as we want. So the whole system is not controllable because x2 cannot be controlled. And let's see that this is kind of black box. We do not know the inside, and what we know is the measurement. Let's say this is kind of black box, and what we know is measurement. By detecting this measurement, can you decide the initial value of x1 and initial value of x2? Not rigorously, just briefly. It can be said, intuitively can be said, given only just the output, can you decide, can you observe the inside states? Can you see what's the x1 and x2 given this y, given this output? That's observability. The definition is a little bit different, but intuitively. If its physical meaning is that, given this measurement, can you take a look at the inside states? But for this kind of system, we cannot see x1 by observing y. So it's not observable, non-observable. So if we have the system model equation, then we may have this kind of state space realization. Okay, this kind of state space realization. So controllability issue is matter of A and B. If A and B has some specific relationship, then from U we can control all the states. If A and B is properly related, then the system is controllable. Observability has something to do with C and A. C is a relationship of state and output. So the state is properly related to the output, and state has some specific transition matrix A, then some nice combination of A and C makes the system observable. Otherwise, the system is not observable. So controllability issue is about A and B. Given U, by setting arbitrarily whatever you want to U, whether we can arbitrarily send state to our desired states, that's the controllability. And observability, controllability is in this equation. And observability is in this equation. Whether we can see inside the states given our measurement. So let's write down the rigorous definition. This is physical meaning, but I need to write down the rigorous definition. Definition of, let's start from the controllability. Definition is quite long. Let me write it down. The state equation. Okay, this is the definition of controllability. Given the state equation, or we don't need the whole equation, we just may need A and B, and the system is called controllable for any initial state, for any final state, if we can send x0 to x1, if there exists such input u that transfers x0 to x1, then the system is said to be controllable in a finite time. So this makes sense with the controllability definition. So let me draw two diagrams that's not controllable. Symmetric circuit. If I say they have the same resistor, 1 ohm, and if I set the voltage on the capacitor as state, and this is input, and this is output, then because these two circuits are symmetric, whatever input U is given, okay, and let's say X initial condition is nothing. So initially there is no voltage. If this is the case, whatever input U is exerted, X is not changing because of symmetry. Voltage is all the same for any input. So we cannot control the voltage across the capacitor. This is uncontrollable system. Another one is also symmetric circuit. Okay, in this case, you might be able to, by adjusting U, you might be able to control X1 or X2. So you should be able to control X1 or X2. But this is OR condition, not AND condition. You can control one of them, but both of them you cannot make it controllable. Or, if the initial condition is nothing, then x1t equal to x2t. Their voltage will be always the same in case its initial condition is nothing. So this kind of system is non-controllable system. So example of non-controllable system. So you have, my major is in mobile robotics. In mobile robotics, we have kinematics of mobile base. For example, there are two wheels, and the state is defined as x, y, yo, and control input is control input on left wheel and control input on right wheel. Then we might be able to write down some kinematic equation, linearized. Then if we analyze the controllability, we can see that given two input, whether I can adjust x, y, yaw as we want, you can see that. That's one of the controllability. If you have omnidirectional robot that has 4 wheels or 3 mechanical wheels, then you also can analyze controllability, whether given two input, whether you can change all the directions, all the XY positions as you want to or not. So if you're interested, just writing down the linear equation and just calculate the controllability. So let me say, when the system is controllable, system's controllability. Theorem 6.1. The following statements are equivalent. First, the m-dimensional, n-dimensional pair A and B is controllable. This statement is the same to n by n matrix W controllable C from 0 to t exponential A tau B transpose exponential A transpose tau d tau, which can be written as t minus tau 2. This is matrix if this n by n matrix is non-singular. For any positive C. Third, controllability matrix. C is defined to be combination of A and B. B, AB, blah blah blah, A, m minus 1 power B. The controllability matrix, its dimension is, what's the dimension? In column, it should be, let's say that control input U has, let's say A is n by, let's say that state is vector of n, and input is vector of p. Then A is n by n matrix, B is n by p matrix. Then B is n by p, AB is n by p, all n by p, and there are n columns, so n times its dimension is n times nb, np. The controllability matrix, dimension n by np, is full rank, has rank n, has full row rank, has rank n, which is full row rank. Every row is independent. And this statement is the same to number 4. N times n plus p matrix, A minus lambda I, B has full row rank for every eigenvalue. For every eigenvalue of lambda, this n by n plus p matrix has full row rank. Finally, this is identical to Lyapunov equation. If all eigenvalue of A has negative real part, if A is stable, then the unique solution of a Lyapunov equation is positive definite. Where WC is the same to WC in the definition number 2, and we say this controllability Gramian. Okay, all statements are the same. And in reality, if you want to see whether a system is controllable or not, which one will be practical? Well, calculating WC is quite burden because we need to calculate exponential matrix T. It seems quite burden. And checking all the things for eigenvalues is also a little bit much calculations. So the simple way is checking the controllability matrix. So given A and B, you might be able to constitute a n by np matrix such that C, and by checking the rank, you can see whether the system is controllable or not. Of course, it can have deficiency. It means it can have rank deficiency. In case of rank deficiency, that means rank deficiency is the same to part of state cannot be controlled. So if it's full rank, it means all state can be controlled. But as rank decreases, that means the number of states can be controlled is also decreasing. So in this circuit, if this is the circuit, then its controllability rank might be 1, not 2. There are 2 states, so n is 2. So here, we are able to control either one of them. Then its controllability, if you check the rank of the controllability matrix, then it will be 1, not 2. So we can control just one state. For this, given this initial condition, the controllability matrix rank may be nothing. I need to check it though. Given this initial condition, it maybe is nothing. So we cannot control anything. There's one state. So in reality, you can check whether you can control a system or not by using that kind of controllability matrix. So one example, simple example is example 6.2. Okay, let's say this is kind of system, given system. Then is this will be controllable? In intuition, just intuition, if there's no tools like this, we may use our intuition that, okay, x1 is function of x2, and x2 can be control input directly goes to x2, so we may adjust x2 in some way. So maybe x1 is also can be controlled because x1 is controlled by x2, and x2 is directly related to control input. So, okay, it seems like the x1 and x2 seems to be controllable maybe. Similarly, okay, x4 is controlled by directly from control input. Okay, so I may expect the x4 is controllable as I want. And x3 is function of x4. So if I can't control x4, I may control x3. Okay, so there are two control input nicely goes to 2 states, so it seems like that may be controllable. Intuition, just intuition. No mathematical or no rigorous reason. Then we constitute the matrix C. First B, 1, 0, 1, minus 2. B. Then AB. AB is, if I multiply it, 1, nothing, minus 2, nothing. AB. A square B, multiplying A to AB. Then nothing, 2, nothing, minus 10. And a cubic B, this times this. Then 2, nothing, minus 10, nothing. Okay, this is controllability matrix. And its rank is, we can intuitively calculate it, right? This is independent, so rank 1. And it seems to be pretty similar to this one, but this is 1 minus 2, this is 2 minus 10. Different information, independent information, rank number 1, one more. And this is far different from others, rank 1 more. And this seems to be same, but far different information, rank 1 more. So each have individual information. So its rank is rank 4. So the system is controllable. So we can send, given any initial condition, any given initial condition, we can send to any arbitrarily state by adjusting u. Then the next question is, what is that u? Okay, I know that, I can find it. I know that. But what's the value exactly? That's the different question. So after taking 10-minute break, we're going to answer how to find u if the system is controllable. My dear, I forgot to turn the power on of this mic. So I need to briefly re-explain what's going on here. Okay, so if AB is controllable, again, I do that one more time. If AB is controllable, then we know that this controllability gradient is non-singular. Then we want to send x nothing to x1. And this xt1 is given in chapter 2 with red part as u. Initially, ut is not written like this. But we designed ut in a way that eliminates those things. In a way that if I write ut up to this point, if I design ut up to this point, then it's wct1, the same to this 4. And I eliminated wc with wc inverse, so eliminate it. And I eliminate initial condition, and I add x1. Then finally, xt1 goes to x1. You can easily check it. So example is, given this kind of a mechanical system, then the state representation is okay, given like this. If we take a look at it, it's pretty easy that it should be controllable, right? Because my control input goes to both states. So I can directly give input to both states. So it seems like that is controllable. And if we calculate controllability matrix, 0.5, 1, and this is 0.25, minus 1, and it has rank 2, so it's controllable. Definitely controllable. So if the initial state is given to be 10 minus 1, and I want to send those states to nothing, I want to stabilize it. Initial condition was some way distorted, but I want to stabilize it within 2 seconds. In 2 seconds, I want to make it in not equilibrium, because there may be possibly velocity, right? Here, just position. Just I want to put it in nothing. If you also want to control the velocity, then you need to specify that as state too. You need to model including velocity, not only the position, but also velocity should be included in a way that x1, x2 position, let's say 3, which is equal to x1 dot, x4, which is equal to x2 dot. You need to design a new system with this new states. If you want to set velocity equal to nothing. If you want to set acceleration equal to nothing, very stationary, then you may add x4 in a way the x1 double dot. In that way, you may expand the state as you want. Then maybe here you may get the control input. We will calculate. That's not made that much difficult. But if you increase the state, the control input may be very strong. It will be the amplitude may be very large. You need very strong motor to enable that control. For this, you may need just light motor, not much big torque. But if you want to make acceleration or even jerk to be nothing within 2 seconds, you may need big hardware. One example is that if you go to elevator in the very good hotel, for example, W Hotel or Shilla Hotel, Lotte Hotel at Jeju Island, you may not feel the acceleration. You will feel it very smooth. But the elevator right on here, you feel that it's jerking, it's zigzagging. You feel all the things in your body. For this building, the motor doesn't necessarily need to be powerful, because doing like this just control the state or even velocity. But if you go to a good hotel, and the motor should be very powerful to control all the things. Anyway, our state is what we want to do is this, and it is not guaranteed that whether x1 dot, if I set the state in this way, it's not guaranteed that whether this is controllable or not. We need to derive another system state space realization, and we need to check it again. So if you want to do that, try it. You may check whether you can smoothly control this system or not. You can do that, given mechanical system. Okay. Anyway, UT is given to be like this: B transpose. First, let's calculate WC. Control with gradient within 2 seconds. So integration 0 to 2 seconds. Within 2 seconds, we want to do something. Exponential A tau. A is from system matrix, tau. B transpose. Exponential A transpose tau. A tau is simply calculated, right? It's just exponential minus half tau, exponential minus tau. So simply calculate. Each term is individually simply calculated, and that calculation gives this value. Then our UT is I will put minus in the front. Minus B transpose. And E A transpose T minus tau. Right. And WC inverse, which is this matrix. And if we calculate it, if I calculate it, it will be exponential minus half 2 minus t, nothing, exponential minus 2 minus t, and this inverse, and exponential minus 1, nothing, exponential minus 2, 10 minus 1. Okay, simple, straightforward calculation. Okay, given this control input, I can make it to a 0, 0 position in 2 seconds. But unfortunately, that may not be the equilibrium point. It's just intermediate point that passes 0, 0 at that time step, but it will vibrating. It was still vibrating. Maybe. So controllability is basically function of A and B. If we think about, this is very nice case because control input goes to both states. But maybe you expect that if this is the case, well, of course it could be again controllable, but it's not that much better than previous case. If I extend it, okay, let me imagine that there are 100 states. So many states, 100 states. 100 states. There are so many states. Then, if there is scalar input, it's just one input, scalar input, and the matrix is given like this, or nothing. Well, they could be possibly controllable if the system matrix is related in a way that x1 is linked to x2, x2 is linked to x3, x3 is linked to x4, and x99 is linked to x1. If all the states are linked directly, nicely, then if I control the first state, then all the states will be controlled. Okay, but that's very special case. In general, A is random and sparse, and it's arbitrary matrix. So if this is the input, then we may imagine that, okay, it seems like that it's not that much effective in controllability point of view. Then you may add more control. You may add more control. Not only one, but also U1 and U2, more control input with more columns, right? Then it will be better to control many states. Okay, you may extend it. Then, what about having 50 control? Okay, then it seems to be nice. Control input, you may imagine that this is number of motors. If we have 100 joints on a robot, and you have 50 motors, then it seems like that it will be controlled nicely, even though the dynamics or kinematics is complex, right? So it's natural that as we increase the p, this is p by 1, this is n by p. As we increase the number of p, then it will be better in controllability aspects, right? This is natural intuition. Then thinking about C, controllability matrix, which is B, AB, A square B, A cubic B, blah, blah, blah. And in this case, 100 state A, 90, B. Okay, if B size is increasing, then its size is increasing. So this is n by p, the size is increasing. Each is n by p. So the whole size is increasing. So whole size is n by np. So intuitively, if we increase the number of states, if we increase p, then maybe we don't need to check them all. This is too long. Too large size. Maybe we may effectively extract core part. Effectively extract, for example, N50, for example, which is B, AB, blah, 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 A45B. If I check this matrix, then we might be able to check whether the system is controllable or not. Maybe. That's the idea. Again, with many inputs, the controllability gradient also increases. But at the same time, if there are many inputs, then we might not be need to check the whole matrix. Rather, we may extract some. We may decrease the size. Decrease the size in some way. And if we check the rank of this, then we might be able to check the whole system is controllable or not. Here, this should have some relationship with P, right? This should have some relationship with P. But rather than P, this should be related to the rank of this. Rank of B. Because P could be dependent, linearly dependent. If they are linearly dependent, it does not mean anything. So, rather than P, the rank of matrix B may have some relationship to this kind of thing. So that's doing those procedure is what we're going to do. That's controllability indices. Did you get it? What I need to explain? Okay, let me reiterate it in Korean, okay? 자, 컨트롤 인풋이 많아지면 좋죠, 그죠? 컨트롤 인풋이 많아지면 컨트롤 인풋의 수는 모터의 수라고 생각합시다. 모터의 수라고 생각하고 스테이트의 수는 관절의 수라고 생각합시다. 그죠? 관절의 수만큼 모터가 딱 제자리에 정확하게 있으면 이거 그냥 아이덴티티죠, 그죠? 다 아이덴티티죠. 그럼 뭐 볼 것도 없이 컨트롤러블 해요. 근데 뭐 연체동물 뭐 이런 거 생각하면 모터 수가 적잖아요. 그죠? 모터 수가 적죠. 혹은 우리 팔을 생각하면 리던던시가 있는 거, 그죠? 뭐 하여간 그런 다양한 변형들이 있을 수밖에 없고. 하지만 컨트롤러블한가만 판단할 때는 U가 많을수록 당연히 컨트롤러블 하겠죠. 그죠? 그럼 U가 많아지면 자연히 P도 늘어나는 건 맞고요. 그죠? 그러면 원래 우리가 컨트롤러빌리티를 체크할 때는 그 P하고 관계없이, 그러니까 컨트롤 인풋이 많냐 적냐와 관계없이 그냥 무조건 A는 n-1까지, 스테이트의 개수 -1까지 무조건 곱해야 되는데 굳이 그럴 필요가 있겠냐. 컨트롤 인풋이 만약에 많아지면 뭔가 이 C라는 오리지널 매트릭스가 아닌 뭔가 좀 작아진, 예를 들어 C50이라고 하면 49까지만 하는, 요거 -1까지만 하는 뭔가 작아진 컨트롤러빌리티 매트릭스로도 컨트롤러빌리티를 판단할 수 있지 않겠냐라는 게 이제 기본적인 인투이션인 거죠. 그럴 수 있겠죠. 그죠? 뭐 모터가 많아지면 당연히 더 컨트롤러블해질 테니까 더 컨트롤러블해진 시스템은 뭔가 좀 더 작은 컨트롤러빌리티 매트릭스만 가지고도 컨트롤러빌리티 체크할 수 있지 않겠냐라는 생각을 할 수 있는 거고, 그런데 이 줄어든 숫자 99, 이거는 이제 원래 데피니션으로 하면 100이죠. 100. 예를 들어 여기에 어떤 넘버를 줬고 여기에 그거 -1을 적는다고 치면 99면 100이고 49면 50이죠. 그러면 이 50이라는 수는 P하고 연관이 있다고 보기보단 이 매트릭스의 랭크하고 연관이 있다고 보는 게 맞겠죠. 그죠? 왜냐하면 P는 똑같은 걸 적을 수도 있잖아요. 단순히. 이거 두 개가 똑같으면 주는 인포메이션이 사실상 없는 거죠. 그죠? 하나하나 두 개는 똑같은 거죠. 그래서 P의 숫자보다는 랭크의 숫자하고 이 뭔가 줄어든 컨트롤빌리티 매트릭스하고 연관성이 있지 않겠냐. 그러면 그 연관성을 뭐라고 하느냐? 컨트롤빌리티 인디시스라고 합니다. 그 연관성을 컨트롤빌리티 인디시스라고 합니다. 설명이 좀 더 됐을 거라고 보고, 질문 일단 여기까지. Okay. So this is motivation of controllability indices, and I will go to controllability indices. Okay, given the system matrix, let's say A is n by n state, and B is n by p. Okay, so there are p inputs. That means B is P columns, B1, B2, BP, P columns. Then C, controllability gradient is B, AB, A square B, blah, blah, blah. So B, B1, B2, BP, this is B, and AB, AB1, AB2, blah, 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 AB, P, and A square, B1, A square, B2, blah, 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 A square, BP, and goes on. 쭉 goes on. And among them, let's select one column. For example, B2. Let's select B2, for example. We can take whatever. Then we may write the B2 terms for, let's say, m equal to 2. So we took B2. We need to write all the B2 terms. B2, A B2, A square B2, A cubic B2, A first power B2, blah, 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 A n minus 1 B2. Then there possibly this and this and this and this, let's say, up to this point, those vectors are linearly independent. Up to this point, each vector are linearly independent. But from this vector, for example, they could be possibly linearly dependent to those vectors, right? Those vectors, of course, it doesn't necessarily to be 3, but let's set it that those are linearly independent, but from these vectors, they become linearly dependent. So from here up to this point, linearly independent. From this point, linearly dependent. Then we say mu 2. Mu 2 is 1, 2, 3, 4. Mu 2 is controllability, one of the controllability indices. So given the second column, if I write all the things like this, then it's independent up to 4 columns. And afterwards, they are dependent. So in this way, we may do that, calculate mu2 and mu1 for the first column, mu2 for the second column, and mu p as p last column. If I write it as a set, then this is controllability indices. This is controllability indices. Okay? Did you get it? Okay, one more example. Okay, controllability indices is, for example, mu1 is 1, mu2 is 2, mu3 is 3. And if I write it, and let's say that n is 5, and let's say the p is 3. So given 5 states, we have 3 control inputs. Then if we calculate the C, B1, B2, B3, AB1, AB2, AB3, A squared B1, A squared B2, A squared B3, A cubic squared, and A cubic, and finally a fourth power. Okay, this is controllability gradients. Oh, controllability matrix. Then, if mu1 is 1, then b1 is only independent. So let me mark red as independent. And let me underbar as dependent. If mu1 is 1, this is only independent, and this is dependent to b1. So I can make ab1 using linear combination of b1. And this is a square b1 is also dependent, so I can make a square b1 using the linear combination of b1. And this is also dependent. This is also dependent. mu1 equal to 1 indicate that. mu2 equal to 2 indicates that first two vectors are independent. So b2 is independent and ab2 is independent. Since then, following a square b2 can be generated from by the linear combination of b2 and a2, ab2. Similarly, a cubic b2 can be generated by linear combination of those two, and a fourth power b2 also can be generated by linear combination of two vectors. In that way, b3 is independent and it's number 3. So this is also independent. This is also independent. But after that, this can be generated by linear combination of those 3. Also, this can be generated by linear combination of those 3. If this is the case for p equal to 3, then we say this mu1, mu2, mu3 as controllability indices, plural indices. We say that as controllability indices. And this is indices, plural. Let's select one of them as mu equal to max, largest one. This is controllability index. It's not plural, it's single. So controllability index is mu, which is the largest value among controllability indices. Here this mu is the least integer. This is the least integer, such that rank of controllability matrix. If I define controllability matrix with specific number, then this is B, AB, and A mu minus 1B. So this is kind of definition. If I put a subscript number, then controllability matrix is calculated up to mu minus 1 multiplication. So total mu columns. So if we take this mu, maximum of controllability indices as mu, then its rank is the same to the rank of original C. So if it's controllable, if it's controllable, mu is the number that C mu rank is equal to n. That means we do not need to calculate a long matrix. Originally, we should calculate not only this, but also originally we were to check the controllability matrix rank to see the system is controllable or not, but now we can do that in a more compact form, shorter, more compact form by calculating mu. Then the range of mu, let's think about the minimum value and maximum value of mu. Okay, mu can be bounded. What's the minimum value? Smallest value. Minimum mu is that if every mu has the same value, every mu has the same value, all the mu have the same value, all the mu I have the same value, then it's minimum. So this is, let's say case A is all the indices have the same value. So mu1, mu2, mu p have the same value. Then A is n by p. This is minimum value. Then what's the maximum value? Maximum value is, if I say case B, all other indices are 1. All other indices are 1. And only one indices are large. All indices are 1. Only one indices, for example, let's say mu p is n minus p minus 1. Oh, I didn't say that the sum of mu p is equal to n. I have to mention that. I skipped to mention that. Mu1 plus mu2 plus mu p equal to n. Their sum should be n. Their sum should be, because the system is controllable, their sum should be equal to the number of states. Why? Because here, if the rank is, it doesn't make sense. It should be 6. It should be 6. Okay, so if the system is controllable, then in C, its rank should be 6, right? That means there are 6 independent columns. There are 6 independent columns. 1, 2, 3, 4, 5, 6 independent columns. So the sum of controllability indices is equal to sum of controllability indices equal to rank. So the controllability index's minimum is n by p because their sum is n. Their sum is n. Sum divided by number. N by p is minimum. And if all the things are 1, so how many 1? There are p minus 1, there are p minus 1, 1. So n minus p minus 1. the one largest is the n minus p minus 1. So one largest is n minus p minus 1. But this is those two kinds are extreme cases. Extreme cases. On the left bound, on the right, upper right bound, and leftmost bound and rightmost bound. But in general, it's on one of the intermediate values. That's case C. Case C is that you remember the minimum polynomial. If n bar be the degree of the minimum polynomial, be the degree of minimum polynomial, then a n bar can be linear combination of previous things. If n bar be the degree of the minimum polynomial, remind the minimum polynomial that we covered in chapter 4. If n bar is the degree of minimum polynomial, then a nth power is linear combination of lesser degrees. So any a nth power b can be generated by the combination of b, ab, a, n minus 1b. So this is typical, maybe typical cases. AB is extreme cases. This may be common and popular and typical cases. So n bar is here. So mu's maximum is one of them, but let's select minimum one, small one. So mu have the range of minimum n by p, and maximum is minimum of those two. But this is easy to calculate. This is if we know the n and p, then that's it. But this is extreme bound. This is difficult to calculate because we need to check the minimum polynomial. But if you try, you might be able to make it. Okay, so after taking 10-minute break, we will see some more things regarding the controllability indices. Okay. So, with those things in mind, let me describe theorem 6.2 is that the controllability property. What do you think about the controllability or controllability indices? They are variant or invariant given some transformation. We talked about many transformations, right? Transformation is basically change of basis, right? So one basis, and we may transform it to the other basis using similarity transforms, right? So if we change the basis, eigenvector possibly change, but what about eigenvalue? Eigenvalue is kind of intrinsic parameter. It's not changing. It's inherent parameter. Eigenvector is also inherent in the one eigenvector is also inherent, but its base is changing like this. So its value is changing, but actually, physically, eigenvector and eigenvalue are intrinsic parameter. It's not changing, but as the basis changes, its representation value is changes. So eigenvector changes anyway. Eigenvector is changing, but eigenvalue is intrinsic. It's not changing. But what about the controllability? if I do the transformation, are they will change or not? Maybe it seems like the intrinsic something, right? So theorem 6.2 indicates that the controllability property is invariant. Under any equivalent transformation. So it's kind of natural consequence. So let's prove it. Controllability matrix is BAB AM minus B, and we have such a transformation P that A bar is PAP inverse and B bar is PB, a similarity transform matrix P. Here, P is non-singular. Okay, we have P. Then, difficult to pronounce it, right? It's difficult to pronounce it. This is okay. A bar, B bar. It will be written like this, and B bar is PB. A bar, B bar is P inverse P drops out, PAB, and it goes on. And finally, we have this matrix. So this is simply PC. So if we calculate the rank of this thing is rank of PC. In this case, if P is non-singular, if this is non-singular, then it does not hurt any rank of C. If P is non-singular, it does not hurt any rank of C. So this rank should be the same to C. For detail, you may see the chapter 3. In chapter 3, one of the statements describe this property. So transformed controllability matrix has the same rank to the original controllability matrix. So it's invariant under any equivalent transformation. One thing is this, and the other thing is not only the controllability property, but also the controllability indices. The set of controllability indices of AB is invariant. Under any equivalence transformation or under any reordering of columns of B. Okay, not only the controllability property, but also controllability indices are invariant under any equivalent transform, under any reordering of column of B. So first, let's say AB, first proof of A. Okay, from this, here n should be set to any number. It doesn't necessarily to be n. It could be small numbers. So we have seen that k k bar. They should be the same. Here, k was n, but it doesn't necessarily to be n. Doesn't matter. We can maybe set it to k. This is good for arbitrary k, k1, 2, 2, 2, p, for any arbitrary k. That means the mu, mu1, mu2, mu p, for each k, this is valid. So mu1 should be the same to mu1 bar, mu2 bar, mu p bar, naturally. So under any equivalent transformation, each controllability indices should be the same. So it's invariant. Regarding the reordering is done by permutation matrix. Reordering is done by permutation matrix M, for example, in such way that, let's say this is B hat. If there's B, we may reorder the column, for example, if I do set the permutation matrix in this way, then columns are changing. Columns are reordered. So reordering of columns. This does not hurt any controllability issue, because if we calculate CK hat, then this is B hat, AB hat, AK minus B hat, where just M terms are summarized, added in the end of original CK. And there are M terms, M on the diagonal. And this is full rank, so it does not hurt any rank. So the rank should be same. Its rank and its rank should be the same. So it's not changing at all. So in conclusion, controllability and the following controllability indices are invariant properties, like eigenvalue. Eigenvalue is invariant properties. Also, maybe eigenvector changes, but relative relationship of eigenvectors. Relative relationship, 45 degree, for example, two eigenvectors, 45 degree. Relative relationship of eigenvectors also, I can say invariant, right? Regardless any basis. So those kind of things are invariant properties. Okay, now let's go to observability. Now we are done with controllability, and now I want to go to observability. Intuition is something that, given the why, whether I can look at the inside of states or not. That's the physical meaning, but rigorously is slightly different. So rigorously, let me write down the definition, rigorous definition. The system is said to be observable. The system is said to be observable if for any unknown initial state, there exists finite T1 such that the knowledge of u and y over 0 to t suffices, suffices to determine the initial state. then the system is said to be observable. So it's slightly different. Okay, we do not know the initial condition. It's unknown variable. We have no idea. But what we know is that for a certain period of time, we have information of control input and measurement. Why? Then, using those informations, if we are able to trace back the time, and if we are able to estimate uniquely determine x nothing using those informations over this period, then the system is observable. Then this 0 maybe can be changed to specific time, right? Other time. For example, I want to know the state at x 0.1, then we can shift the whole system by 0.1 second. So we can set this x prime shifted system. We can shift it. Shift the transition is simple, right? Then by shifting the time frame, we may inspect the state. We may see how the state goes on. So physically, this means that I can see inside the system. I can see the value of states for a specific time of my interest. So that's the observability. One very nice property of this observability is that all the properties of controllability is dual. It's like mirror, dual. So all the properties are valid by doing a simple transformation that okay, let's define a observability gradient. First, let's define observability gradient as W nothing. Let me write it down, the theorem. The state equation is observable if and only if the n by n matrix observability gradient from 0 to t is non-singular for t positive. Okay. In theorem 6.5 is proof of dual. The pair AB is controllable if and only if the pair A transpose B transpose is observable. This is duality, about duality. Controllable, if this is controllable, that's the same to its their transpose is observable. So controllability and observability is basically has duality relationship. So all the properties of controllability something is hold for in observability by doing just simple transformation, simple transpose. Because our controllability gradient is 0t E A tau B B transpose E A transpose tau d tau. And see, the observability gradient is transpose here. So instead of A, I may put A transpose. First I will write it the same copy to the uppercase. Okay, this is the same to WC. Observability gradient has transpose here, so I put transpose. And transpose in the first. And here, transpose is nothing. And transpose is nothing. So if I take B to B transpose, A to A transpose, then original controllability matrix becomes observability matrix. So it's simply transpose relationship. So if I change A to A transpose, B to B transpose, then original controllability matrix is changed into observability matrix. So all the properties valid for controllability something 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 is also valid for observability something something. So by the duality, we may write properties of observabilities without proving them. So, without proof, I recommend you to inspect theorem 601. And corollary 601 and theorem 602 and theorem 603. They are just simply reiteration of the controllability issue after doing transpose. So we don't need to mention it in detail. Just reading them through is basically the proof is all the same. All the things are the same except it's transpose. But there's one difference. One difference between controllability and observability is that how to calculate, how to find in controllability, when we do the controllability, we set ut to send the x0 to x1. There is a specific way of finding ut. Similarly, in the observability, how to get x nothing given the information. This is different thing. Other things are the same basically because of duality. Okay, let's take a look at it. How to find x nothing given control input and t for a specific time being. Y, control input and measurement for a specific time being. How to trace back, how to identify the initial condition. The output YTA is basically CXT, right? It's CXT plus DUT. And XT is, we know the solution, differential equation. Solving the differential equation, XT is given to be EAT x nothing plus 0 to t EAT minus tau B u tau d tau. Okay, xt is given to be this. So yt is cxt, cxt plus dut. Then let me send this to here. Yt minus c equal to c e a t x nothing, and let's denote all of them as y bar t. Then determining x nothing is, if I say this is a matrix, what shall we say? mx equal to some specific measurement, b. mx equal to b, simple, ax equal to b4. Nothing more than that. Ax equal to b4. mx equal to y, let's say, y bar. This is mx equal to b4. So, if m is non-singular, then x is straightforward, m inverse y bar, right? If this is non-singular, straightforward, x can be uniquely determined. But, in general, if I think about dimensions, y dimension is, let's say, y dimension is q by n, if I say, u dimension is p by 1. Y is q by 1, I'm sorry. Q by 1. Then c is q by n. This is n by n. So the whole matrix M is q by n. Q is number of measurement and n is number of state. In general, which one is large? Number of measurement versus number of state. Which is large in general? State is large. Number of state is large. In general, this is the case. If this is the case, there should be null space. Rank deficiency, null space. If there is null space, multiple solution. So in general, this equation gives multiple solution. So, what can we do is this. We do not do that for a specific time being, but we accumulate information as time goes on. So we accumulate the information for y t1, for y t2, blah, 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 for y t specific time k equal to m1 time t1, m2, m3, blah, 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 mk, and x nothing. Then, this is kq by n. So, we have k more measurement as time goes on. Then, possibly, its rank can be full because of this accumulation. Then, we might be able to determine x nothing. So, when you calculate x nothing, not only for the specific time being, but also accumulate them as time goes on and make the matrix full rank, then get it. Okay? That's the one difference between controllability and observability. Other issues are basically the same. And my final remark is that this definition can be modified in a way that the system is observable if and only if the initial state can be uniquely determined from its zero input response. This definition is reiterated as a system is stable if its initial state can be uniquely determined from its zero input response because of this equation. Its initial state can be determined. Original definition is from this term, from all those terms, right? Original definition is from all those terms. Modified definition is zero input response. So, if this is zero input response, this drops out. So only YT is good enough. So if zero input response, this is zero input response, no UT. Then if the unique X nothing can be determined from zero input response, then the system is observable. So we can reiterate the definition in this way too. So the system is observable. In this case, also slightly changing if the system is observable if and only if X0 can be uniquely determined from the zero input response. Okay, so we are done with controllability and observability, and in the next class we're going to see using controllability and observability, we're going to decompose the original system, controllable part and non-controllable part, observable part and non-observable part. So we're going to cover the remaining part in the coming class. Okay.